Really? Open. Okay, here we are for precipitation reaction stoichiometry. It's time to move past stoichiometry and apply it to a type of reaction you're going to see over and over in this class. So first of all, if there's a precipitation reaction, we need a balanced equation. So we have barium chloride reacting with sodium sulfate. Make sure that you write your formulas correctly or you're going to have a really hard time balancing this equation, right? And then I get 2 sodium chlorides and 1 barium sulfate. So which one is the precipitate here? Do you remember the solubility rules? All of the chlorides are soluble except for silver, mercury, and lead, and I don't have any of those here. So this is not a precipitate, it's aqueous. But the sulfates have 6 exceptions: silver, mercury, lead, and also barium, strontium, and calcium. Therefore, I know that barium sulfate is my precipitate. So now the question is, how many grams of precipitate will form? Well, I'm going to start with what's given to me in the problem. 10 milliliters of 0.25 molar barium chloride and 10 milliliters of 0.35 molar sodium sulfate. Since they give me 2 amounts, that means this is a limiting reagent problem. So I'm going to have to do 2 t-tables to solve this. So here we go. 10 milliliters, I'm going to convert that to liters right away, is 0.010 liters. And that's barium chloride. So 0.25 molar means 0.25 moles for every liter. Remember, cross out the big M and write moles over liters in its place. And that was barium chloride. I better keep track of what's what here because I need to turn it into my precipitate, which is barium sulfate. So for every 1 mole, for every 1 mole of barium chloride, I get 1 mole of barium sulfate. So far, so good? Great. Next, let's change moles to grams. So 1 mole of barium sulfate is how many grams? Well, I don't know. Let's add it up. Okay, so barium sulfate weighs 233.3 grams per mole. And now we're ready to multiply across the top and divide by what's on the bottom, which is all just ones. How handy is that? So I get 0.58325 grams of barium sulfate, but I'm not sure if that's actually the answer yet. I'm going to work the other t-table and see which thing runs out first. So now let's start with 10 milliliters of sodium chloride. That's 0.010 liters, and it's 0.35 molar. So 0.35 moles of sodium. Oops, I said chloride. It's sodium sulfate, pardon me. And that's for every liter, because that's what molarity means, moles per liter. So liters cancels, and now I have to change moles of sodium sulfate into moles of barium sulfate. And my balanced equation says that that is a 1-to-1 mole ratio. So that's going to make my math easier, right? And now I need the molar mass of barium sulfate again, 233.3 grams. So now we'll multiply across the top and divide by the bottom and see which one made more, the sodium sulfate or the barium chloride. So it looks like my limiting reagent was the barium chloride, right? Because that made the least amount. So my answer to the question, how many grams of precipitate will form, is 0.583 grams of barium sulfate. Now the follow-up question says, what are the concentrations of all the ions present? Well, concentration specifically is referring to moles per liter, right? So I need moles of each ion divided by the total liters of everything that I mixed together. So my total volume is equal to 10 milliliters plus 10 milliliters. So I have 20 milliliters total, which in liters, 0.020 liters. That's my total volume. I'm going to use that in the denominator of all of my ions. which ions do I have in solution? Remember we went over solubility rules. Everything that's soluble is actually going to break apart into ions. And everything that is solid is going to stay together. So I'm going to see here, this breaks into a barium 2+, and not one chloride, but 2 chlorides, right? Because BaCl2. And then I get 2 sodiums for every sodium sulfate particle, and 1 sulfate ion. And so let's see, I used up all of my barium chloride. This was my limiting reagent. So do I have any barium ions left in my solution? If I used it all up, that means none of these are left. How about the chloride ions? Are any of those left in the solution? Well, that ran out first, but what did they do? Chloride on the other side is just a spectator, right? Look, I have 2 sodiums hanging out here, and I have 2 chlorides. They're still there. They're still in the beaker. So I have to calculate their concentration. And the barium sulfate is all stuck together. All the bariums got used up, but the sulfates, I'm going to have some left over. So I have to do an excess reagent, plus I have to solve then how many are left behind. This might take a little bit of time. Don't worry, we're going to take it one step at a time. So let's start with sodium. Volume times molarity equals moles. So yeah, let's start with sodium. Might as well. So I have 0.010 liters of sodium ions, of sodium sulfate. And there's 0.35 moles of sodium sulfate in every liter. And then remember, too, that there's, for every 1 mole of sodium sulfate, 2 moles of sodium ions. So I take 0.01 times 0.35 times 2 to get my sodium ions. So that's 7 times 10 to the minus 3 moles. Now I need moles per liter. So the concentration of sodium ions in my resulting solution is going to be 0.007 divided by 0.020 liters. So that's moles per liter. And that gives me 0.35 molar Na+. So I'm going to keep track of that up higher because I'm going to need the room to write the next one. So the concentration of sodium ions was 0.35 molar. Let's work through the next one. Okay, the next one I want to do is chloride because all of my chloride is still left. None of that got used up. So I'm going to start with barium chloride, 0.010 liters of barium chloride. And I had 0.25 moles per liter because that was my molarity. And for every 1 mole of barium chloride, I get 2 moles of chloride ions. All right, time to apply the calculator to this one. So I have 0.005 moles of chloride ions. Now let's do the concentration of chloride ions. So I have to do moles per liter. I have 20 milliliters total. Oh, I'm sorry, yeah, 20 milliliters is 0.020 liters. Hey, it's 0.25 molar. How about that? So I know my concentration of sodium and my concentration of chloride. The sulfate is going to take a little bit longer. So let's keep track of chloride ions. It's 0.25 molar. And sulfate is going to take a little longer because it's my excess reagent. So let's see, how much moles did we use up? So barium chloride ran out first, and I just calculated the moles of barium chloride. So that was 0.010 liters times 0.25 moles per liter for barium chloride. And for every 1 barium chloride, I got 1 mole of sodium sulfate. And in every mole of sodium sulfate, there's only 1 mole of sulfate ions. So let's see how much sulfate ions got used up in this reaction. So I have 0.0025 moles of sulfate ions were used up. How many moles did we have? Let's do volume times molarity right here. So 0.01 times 0.35 is 0.0035 is what we had. And we used 0.0025. What's left? 0.035 minus this is 0.0010 moles of sulfate ions remain. And now I do my concentration. Concentration is moles per liter. So the concentration of sulfate ions will be 0.001 moles divided by 0.020 liters. I get 0.05 molar concentration of sulfate ions remaining in the solution. So let's write that up here. The concentration of sulfate ions that remain is 0.05 molar. So now here's my answer to the second part of the problem. Let's do one more, and then you can practice the rest on your own. So here's another reaction that's a precipitation reaction. You better know your solubility rules so that in our balanced equation we can identify what is aqueous and what is solid. Let's start off with the sodium phosphate. Remember to crisscross your charges. Sodium phosphate, and that is aqueous because alkali metals are always aqueous. And then we have copper 2 chloride, so the type of copper that has a 2+ charge, right? Copper 2 chloride. Chlorides are all soluble except for silver, mercury, and lead. So copper's not one of those. That one's aqueous. We're going to form sodium chloride, double replacement reactions, right? Sodium chloride is aqueous. And then copper phosphate. It's copper 2 phosphate, so I got to crisscross those charges. And phosphates are usually solid. Only the ones with alkali metals are aqueous, generally speaking. Now I have to balance this. I need to balance a 3 and a 2 at the same time. So I'm going to use 6 here. That means 3, 2, and that ought to take care of it. What do you think, guys? Does that look good? You better be telling me if I make mistakes in a podcast. All right, how many grams of precipitate will form? So we're looking for the one that is solid, the copper 2 phosphate. So there's my copper 2 phosphate. What do I have to start with? One number or two? Right, 2 numbers. If you're starting with 2 numbers, that means you're doing a limiting reagent problem. So 50 milliliters is 0.05 liters of sodium phosphate, Na3PO4. Use your molarity next. Big M means moles per liter. So I have 0.10 moles for every liter of sodium phosphate. Now I'll use the mole ratio. For every 2 sodium phosphates, we get how many copper phosphates? Just 1. And then we're going to turn this into grams, and then we'll compare with the next T table and see which one made the least. I did not do this molar mass yet. Let's add it up. Copper 63.5. And there's 3 of those. 2 phosphoruses. And 8 oxygens. That's a big sucker. Okay, so 380.65 grams for every mole of copper 2 phosphate. Got room for this? Maybe. All right, do the top times the top and divide by the bottom. I got 19.1 grams of copper 2 phosphate. Now let's see the other one. We'll compare, see which one makes the least. So 50 milliliters again, and that is copper 2 chloride this time. And I had 0.10 moles per liter because the big M means moles per liter. And that's my copper 2 chloride. So let's use our balanced equation to write the mole ratio. For every 3 copper 2 chlorides, I get 1 copper 2 phosphate. And now we need the molar mass again, but it's the same stuff as it was before. 380.65 grams. All right, let's work it out. That's 5.1. So that's only 0.6344 grams of copper 2 sulfate. Now, just to be sure, I'm going to run this through my calculator again. Yep, sure enough. Okay, so here's the answer. The limiting reagent must be copper 2 chloride, right? Because that one made the least. So here's my limiting reagent. And now we get to do the concentration of all the ions present. So I know that the copper went away, but let's list out our ions. I get 6 sodium ions out of this piece, and 2 phosphate ions. Since sodium phosphate is not my limiting reagent, I'm going to have extra phosphate hanging around, so we'll save that for the last. That's an excess reagent problem. Then I have 3 copper 2 ions and 6 chloride ions, and that turns into 6 sodiums and 6 chlorides, and then copper 2 phosphate stays together because that's my precipitate. It does not dissolve in water. And when we say it doesn't dissolve in water, what we mean is the water cannot rip it apart into the ions that it was made from. So let's get our total volume. If I mix 50 milliliters with 50 milliliters, then my total volume is 100 milliliters, which in liters is 0.100 liters. That's our total volume in the end after we mix everything together. So now I need moles, So I can do concentration in moles per liter. Ready for this? I know it's a lot of work. This is our last one for this podcast, so do it. No whining. Let's start with sodium ions. Might as well, right? So my concentration of sodium ions, first I need my moles. So take your volume times your molarity. And that's going to give us moles. Like 0.005 moles. And then we'll divide by the total volume. So the concentration of sodium ions, I'm going to keep track of it up here, is 0.05 mole. Now let's do copper. Do I have extra copper? No, copper was a limiting reagent, so I don't have any copper left. Those ions all got captured in the precipitate. How about chloride? I'm saving phosphate for last because it's an excess reagent. So let's do chloride ion concentration. So moles will be volume times molarity. Volume times molarity. And that is of copper chloride. That's where my copper or chloride ions come from. And, oops, I gotta remember to double this because every copper chloride has 2 chloride ions in it. Did I do that for sodium phosphate? I think I skipped that part. Oops, so fix that. Good thing we go back and double check, right? So 0.05 liters times 0.10 moles times 2. And then I'm going to divide by my total volume so I can get my molar concentration. So chloride ions is 0.1 molar, just like my sodium ions were 0.1 molar. So let's keep track of that up here. Chloride ion concentration is 0.10 molar. Okay, last one is the phosphate. So we have to do excess reagent problem. So I'm going to start with copper chloride, 0.050 liters of copper 2 chloride, and 0.10 moles per liter of copper chloride. And for every 3 moles of copper chloride, I used up 2 moles of sodium phosphate. And I'm almost done. For every 1 mole of sodium phosphate, I get only 1 mole of phosphate ions. So I had 0.00333333 moles of phosphate ions. Now I have to do the molarity. So for molarity, we do moles per liter. So 0.003 divided by 0.100 liters. And that gives me a 0.033 molar solution of phosphate ions. So now I've answered all the parts of the question, and it took a lot of work, but it's not hard work. None of the steps were hard. You just have to do a lot of steps. But hey, that's AP Chemistry. So we'll practice this in class, and I'll see you guys soon.